All right, so I want to talk a little bit about regression and trying to identify a few things on the template that was provided. So just quickly to go over this, the equation for the population is given by what's shown on the screen. Y equals beta naught plus beta 1 x plus epsilon. The epsilon again is in some error term. So conceptually, we think that y is related to x in some fashion, actually a linear fashion, as expressed by the equation. But we don't know what beta naught and beta 1 are. They're population parameters, kind of like mu before, and we don't know what they are. So we're going to use some data to try and figure out what they might be and get estimates. And those estimates, we're using the terms b naught and b1 to reflect those estimates or to represent those estimates. So we end up with an equation y hat equals b naught plus b1 x. So with that though, whoops, skipped the page, aren't you there? Sorry. So with that though, beta 1, if that is 0, that means there's no relationship, right? Slope of 0, you can just go back and plug in on the previous page even. If beta 1 were 0, you just have y equals beta naught plus epsilon. So no relationship. So that would be the interpretation of beta 1 being 0. So, but our estimate of beta 1, which is going to be the b1, it's never going to be 0, even if there is no relationship. And just quickly, give you some idea about that. You'll find variables out there in the world that have a correlation, but there really is no true underlying relationship. They just happen to be showing up as some relationship. And to give an example with that, let me just pop up here. Whoops. I've got this website here that shows some spurious correlations, right? So between U.S. spending on science and space technology and suicides, and looks like they're related, but they're probably not. There's probably not much of a true relationship. So, so we're going to conduct a test of the hypothesis that the slope is 0, that there's no relationship. So previous to similar tests that you've done for the population mean being a certain value, you can use a t statistic, or if you think about ANOVA, there was an f statistic, and with both of those we had a p-value. We're going to use those same tools in conducting this test. If we reject the null, so we have a large statistic, a large t statistic, or if it's negative, it's very small, so large negative value, or a large f statistic, or a small p-value, then we're going to end up rejecting the null, and that means that there is statistical evidence that the slope is not 0. But if we wind up with a large p-value or a small t statistic, it suggests that there is no relationship. Now, with that, one other item here that we have is that someone asked about is this idea of a standard error. Well, if we had two different data sets, we'd get two different estimates for the slope, even though the true population slope is one thing. Different data sets will give us different estimates. So these estimates are going to be spread out. So we could have a small standard error or a large standard error. That's the standard deviation for this distribution of the parameter estimate, the B1. In that, thinking about the test statistic for the null hypothesis that the slope is 0, it's just going to be our parameter estimate B1 divided by the standard error. How does that look in the template that you've seen? Well, if I'm coming to this template, we've got some data, 1, 2, 3, 4, 5, 6, and then I can come over here and just plug in some numbers, 2, 2, 4, 4, 5, 5. And on this screen, then that you're seeing. It gives an F statistic right here, and it also gives a T statistic here. These two statistics test the same thing. They're testing the null hypothesis that the slope is 0. This p-value goes with this test statistic. So this p-value here is just found by using this t statistic. And these things tell us to reject. Now the template also gives you that information. It says reject and reject here. This F statistic and this T statistic will always give the same answer. So where does the standard error come in? Well, let me just plug into this cell and show you where this T statistic is coming from and how it relates to the standard error. The T statistic comes from B1, that's this number here, divided by the standard error, that's this number here. That is the T statistic. You can see that these numbers match, 5.458, 5.458. So that's how the standard error relates to the test statistic. The test statistic here, the T statistic, the p-value, and the F statistic can all be used. They all tell us the same answer. They tell us whether we reject or fail to reject. In this case, the numbers seem to work together to give us a reject, because I typed in increasing values here, and then these similarly were increasing in that way. So that just meant a positive correlation, but something where we might see no relationship. I'm going to change some of these numbers, and I'm going to make it come out to be fail to reject. So if this was 2 and then 1, 4 and then 3, 5 and then 6, I guess that's not enough of a difference. It did make the p-value go up, but I guess by not enough. So let me just actually make this one. There we go. That did the trick. So just by changing these numbers a bit here, right, this suggests that there's no relationship, because actually I made the largest value of y have one of the smallest values of x. And what do we see? Small f statistic over here, small t statistic, large p-value implies that we fail to reject the null hypothesis. So hopefully that helps a little bit just in reading what's going on in this table and understanding how that relates back to the concept.